well, let's get officially started then. Good morning, everyone. We are working on partial differentiation. And so that's what my goal today is, to show you some examples of that process, maybe get a little bit more difficult ones that can happen, more complex ones. But let's start off with a relatively straightforward one. Here is a multidimensional function, x e to the power of xy. And I want to find the partial derivative with respect to x. Now, when you look at a question like this, any of these questions, I think the first decision you've got to make is, what differentiation technique am I going to use? Is it simply just going to be a power rule, right? Add, multiply by the power and reduce the power by 1. Is it going to be a product rule, a chain rule, a quotient rule? What's it going to be?
Product.
If you nailed it. Product rule. What about this tells you it's a product rule and not anything else?
There's an x times an e raised to the power of x.
So there are two separate pieces that have x's in them, right? And they're multiplied. If this question had been x over e to the xy plus 1, it would have been a quotient rule, right?
Mm-hmm.
And so you've got to be able to understand what technique, what differentiation technique, otherwise you won't get the answer, of course. So f dash g plus f of g dashed. And then you have to remember that in partial derivatives, x is the only variable in town. Any number or other letter, in this case y, is just treated like it's a constant. So if you differentiate x with respect to x, you get 1. You leave the second guy alone, you get that. You leave the first guy alone, and now you're going to differentiate that guy with respect to x. Well, if you differentiate e to the xy with respect to x, you do get e to the xy. Technically, this is a chain rule, isn't it?
Yeah.
So you finish with a times the derivative of xy with respect to x, which is where that extra y came from. You all comfortable about where that extra y came from? So you plug it in here, and then you do style points. And style points, in this particular case, would be to pull out e to the xy as a common factor. Now, you might get a question, that looks like that. And you might be thinking, what are they wanting me to do here? Well, essentially, they still want me to find the partial derivative, but they want us to evaluate it at the point 0, 1. In other words, x is 0, y is 1. So I already have the answer part, right? Now I make that e to the 0 times 1, 1 plus 0 times 1. Now, e to the 0 is 1, 1 plus nothing is 1, the whole thing is 1. So the answer to what is the value of this, it's 1. If you're wondering what does that look like, can you imagine this being a surface, right? Some kind of flowing surface. At the point 0, 1 on the floor, you go up and you touch the surface at that point. Can you imagine slicing that surface parallel to the x-axis? You get a curve. At that point on the curve, the slope would be 1. So if you're trying to visualize, what does that 1 tell you? It's the slope of the derivative of the curved surface cut parallel to the x-axis. If you have to know what it is. Me, after a while, I just think of it as, hey, the answer's 1. Let's move up the food chain and look at calculating some weirder derivatives. So how about this one? Oops, try that again.
So when you take the derivative of e to the xy with respect to x, the
Mhm.
y drops down because it's viewed as a
constant,
variable, not a variable, but just a
a
constant.
number. Yeah. So if you
Okay.
differentiate that,
Yep.
you get e to the xy times y. If you're not sure what's going on, think of the y as being 5. And if you
Okay.
said differentiate this, you would say, oh yeah, e to the 5x times 5. Well, that 5 is really the y.
Okay.
So that's what's happening, right? Now, how about this fella? Yeah, and feel free to interject like that. I like that. Right. Square root of x squared plus y squared plus 5. And I would like to know the partial derivative with respect to x. Well, the first thing I would look at this question is, well, what technique am I going to use, which is for sure. But before I even get to that, I have to realize that square roots need to be written as fractional powers. Because if you're going to differentiate something, you never leave them as square roots. Don't you turn them to half powers? Because that's what you have to do algebraically to make the power rule work, right? So I'm looking at this question and I'm looking at it as if it was this fella, because this helps me. And then I have to decide product rule, quotient rule, or chain rule. Sometimes you end up doing two rules, but right now, which of those 3 rules is a candidate for this fella's derivative?
Power and chain.
Right, so it's a chain rule that happens to use powers, right? Great. So the rule is multiply by the power and reduce the power by 1. So take 1 away from that and you get -1/2. And it's a chain rule, so it's times the derivative of everything inside the brackets with respect to x. And that's, in this case, it's 2x. Now you might say, great, I've done it. Let's see the next question. But style points kicks in. Would you agree that is a pretty ugly looking answer? And it should be able to be reformed in a way that looks nicer and easier on the eye. And the first thing I would say is 1/2 times 2 cancels out and you get an x. And that -1/2 power looks better as a positive 1/2 power on the bottom. So I'm just doing some algebra there. Are you happy with what I did on that line? And one of the rules of style points is make the answer look like the original. Remember the original was this ugly square root? Isn't this a 1/2 power converted back into its square root? Now, when you look at this answer, that's the one I call the style point answer, right? That's the one that gets all the good looks. Plus, in that form, it's much easier to deal with what might come later. I know we aren't having anything that comes later, but eventually there will be. Now you've got the derivative, do this. For instance, if I wanted to calculate this derivative as an exact value at 1,2, wouldn't it be much easier to get a nicer looking answer in this form than if I left it in this form? If I was wanting to find when is this derivative equal to 0, isn't it easier to solve that problem when it's written like this as opposed to written like that? I'm trying to sell style points, even if WebAssign is quite happy to take some ugly mess. That's because WebAssign is a program. It's not a human being, and they don't always program them with enough subtlety to realize what a better version of the answer is. So our goal is, this is the guy I want to see, right? This is your goal. So don't just do one line and, I'm finished. Bad math to do that. Pretty cool? Now, let's see we can up the ante a little bit more, do some a little bit. Sometimes the simplest looking ones cause the greatest amount of problems to your brain. And I would like, well, let's do y for a change. Product rule, quotient rule, chain rule. Who are we looking at here?
That's a quotient rule.
Pretty obviously a fraction with y's on the top and y's on the bottom. Agreed? Now, if you're going to be that, which you are, then the whole top is going to be called f. The 2 bits in the bottom are going to be called g. And we have essentially a formula. It says f dash g, take away f of g dashed, all over g squared, right? That is the quotient formula. Now, the rule for partial differentiation is still true. Isn't the only variable in town right now y? Right? Every other letter is treated as a constant. What about the A, B, C, and D?
Constants.
Yeah. In fact, aren't they always constants even in a non-partial differential world? Right? So we typically, the convention is if you see an A, a B, a C, or a D, it's treated as a constant. Right? Even in Calc 1, that would be true. So, differentiate the top with respect to y, get nothing out of that, and you get a b. Leave the second guy alone. Subtract. Leave the top alone. And differentiate the bottom with respect to y, and you get that. And the whole thing is over cx take away dy squared. Okay. Do you think I'm going to leave that guy alone, or am I going to do some style points on him? Just looking at him, what do you think?
I think you're going to do some style points.
Yeah. Oh, by the way, you will find as you come through this class, I make up names for things. Don't go searching on the internet for helping doing style points, because who knows what the heck you're going to find, but you won't find what I've got. I just make this name up. It gets across what I'm after. Right, so here goes. Distribute through the b, cbx, take away bdy. This and this cancel it, make that positive. So it's plus adx plus bdy, still over that guy squared. And hopefully, you'll notice that those two guys cancel out. And I basically got CB plus ADX all over CX, take away DY squared. Are we cool with that question? Right. Let me scan through some of the homework, see if anything comes to mind that I've not covered yet, because I know I've got lots of ones. Oh yeah, I have to change some letters of the alphabet. Yeah, we can't just use X's and Y's. That's definitely
So if
something I
you're
need to do.
following along
Yes, Brooke.
in the book, about where at in the book are you?
I'm on section...
Like the online textbook?
Yeah, I'm section 14.3, is it? Let me check my brain. I can't remember. I'll tell you right now. We're in 14.3 in the textbook.
Okay, because
If
mine's
that's what your
talking
question
about.
was.
Yeah, because mine shows some limits and stuff like that for right at the start of 14.3.
I
The
don't
limits
know
and-
what it's doing. I don't really care. I don't use the textbook much. I mean, it's a good
Okay.
resource.
I just didn't know. I hadn't fully looked at the homework assignments or anything, if it follows like your format or the textbook's format.
I tend to follow the topic format. In other words, we're doing partial derivatives right now. So that's what this is. So they do follow into the main section. So you'll find a section called partial derivatives.
Okay.
What you'll find is that the textbook, oh God. If you've done calc before, I'm sure you have, but if you've looked at calc textbooks before, they do an awful lot of in-depth theory of this is why this works. This is it being proved to you. So, I mean, for instance, do you know how we use the product and quotient rule? A lot. If you went to a textbook, they would actually have a 2-page proof of the product rule, which is
Okay.
nice to know, but totally not much help if you want to differentiate anything with the product rule. Isn't product rule a process that you learn how to do, right?
Yeah.
So I suspect what you're looking at there is the theory behind why partial derivatives work and how they get you to the final answer. But in practice, the process is much more important. But it's good to know. I mean, some people don't like magic and understand that. So they don't like you saying, well, you're doing this, how can you get away with it? Well, that's the section I would direct them to. Right, I'm trying to find some weird that we haven't done here. And the best I can do right now is a change in letters. Just randomly picking a weird looking function. And let's change notation so we don't get too caught up with one particular notation. When you see me writing this, isn't this just find the partial derivative of f with respect to x? And this one is do it with respect to t. Okay, just in case you see that notation. Now, if I was going to do this guy with respect to x, the differentiation technique is actually going to be different than if I do it with respect to t. And it's pretty obvious, I think, why. Isn't there only an x squared here? So when you're doing a differentiation with respect to x, you might want to look at that in a different way. Whereas if you're doing it with respect to t, do you see there's two different locations? There's a t squared on the top, and there's an e to the t in the bottom. Secondly, I would look at this question, and I would, me personally, would rewrite it like that. Any ideas why you think I'm writing it this format rather than that?
Then it becomes a product rule rather than a quotient rule problem.
And would you agree that product rules are just easier to live with and deal with?
Yes.
Right. And so if I really wanted to go full hog, couldn't I then rewrite it like that?
Yes.
And now when I ask you to find this one, won't you say, well, that's ugly, but it's nothing, right? It's differentiate with respect to x, at least it's nothing. And this guy here gets me 2x e to the negative t. And for time reasons, I'm not going to do this one, but if I was doing this with respect to t, wouldn't you have two separate questions, really? You'd find the derivative, partial derivative of this term with respect to t, and then this one. This one here would be what, a product rule? And off you go. So there's no reason in the world why the letters have to be X and Y, right? They could be U, V, W as well. They're okay. Let's try this fella. I'm going to show you a little trick here with the trade. And it's a concept called symmetry. Some functions, most of them don't, but some really lucky functions have what's called symmetry. So I'm going to give you some examples of functions that have symmetry. Now, when you look at those functions and you're saying, I wonder what makes a function symmetric. And the rule is basically, if you can take the x and the y, and can you imagine all the x's becoming y's and all the y's becoming x's, you end up with the exact same thing that you started with. So if you can imagine me calling these functions f of x, y's. Well, in this case, uv. Right. What would happen if that became y and this became x? Well, you would end up with y squared plus x squared add 4, which, just with a little rearranging, isn't that back to the start? That makes this function symmetric. Can you imagine that you replace the x with y and you swap the y with x? Wouldn't this become y squared x plus x squared y? And isn't that the same as this guy? And if you made this, it would be v plus u over vu, but isn't v plus u just u plus v? And vu is just the same as uv. So why is symmetry useful? Well, what it does is it allows us to save time. That's it. And there's probably a page of proof in the textbook to show you why this is allowed, which is nice if you want to look at it, but I don't. I like using it. So let me show you that happening. Let's take this one. Is it not virtually identical to one of the questions we did today?
Yes.
Right. In fact, now I remembered that. Can I change that to 5? And that will make it the question that we did today. Right, I think that's the only difference, isn't it? Now I'm going to quickly find that guy's answer. Here it is. Right. So if you want to do the partial derivative with respect to x, the answer ends up being this guy. I am now going to tell you the answer to the partial derivative with respect to y without doing all of this again. Just telling you the answer right off the bat. And the reason I can do that is because of symmetry. Anybody want to have a guess at it? What do you think the answer might be?
I have a guess.
Go for it.
Y over root x squared plus y squared plus 5.
And you're right. What did you do?
I knew that everything under the root was going to remain the same due to the chain rule. But when we differentiated what was under the root, we were going to get lose one of the squared terms and also the constant. And since we'd already gotten x out, I figured we'd get y.
Ah, you're right. Now, let me condense that into a simpler pattern, but you're totally right what you said. If a function is symmetric, their first derivatives will be similar in structure. All you do is take this guy, right, the answer that you know, and replace every x with a y. Switch places. So won't that x turn into this fella? And won't that become y squared plus x squared plus 5, which is this guy? Pretend I have a symmetric function. And in this symmetric function, the derivative ended up being that. So the original function was symmetric, and this was its first partial derivative. Then I can predict what the other partial derivative is going to be, because all you do is you switch every x for a y. So let's see what that looks like. That guy becomes y, that guy becomes x squared, and 5 is still 5. And x squared plus y cubed becomes y squared plus x cubed plus 5, to the power of 10. Do you see how that little trick, little shortcut, allows us to get the second partial derivative by only knowing that the original function was symmetric? The partial derivative doesn't need to be symmetric. Only the original function. And if it is, you can cut down on some of your workload. So it's not earth-shattering if you don't want to use symmetry. But can you imagine it's a really ugly function and you took 5 minutes to differentiate it? Wouldn't it be nice if you could get the second answer like in seconds, rather than having to just start from scratch and differentiate, partial derivative with the other variable? So here is my new guy in town. And we are going to find both partial derivatives. Is this function symmetric?
Yes.
Right. So most of the homework, don't they ask you to find all the first derivatives, not just with respect to x, but they also want you to get with respect to y. So it's a pretty common question to be asked to find both, right? So I have to do the first one the normal way, right? The usual way. But shouldn't I be able to get the second one for free? Right? Because it is symmetric. So here goes. If you want to differentiate a natural log, isn't this a chain rule? And differentiating a log gets you 1 over the thing times the derivative with respect to x. Not a lot of style points here. But there's our answer. So if you want to find the partial derivative with respect to y, you should be able to use this to get that. Great. And for some reason, I lost a 3 there. There we go. So what's the answer? Eleanor, I'm going to put you in this spot. What's the answer?
Is it 3y squared over y cubed plus x cubed plus 4?
Yes. And I'm just rewriting the x and y. What you said, right? Do you like the symmetry trick? In this case, it's such an easy derivative, it probably didn't save you any time at all. But can you imagine in the grown-up world where it's a really, really ugly function, but at least it's still symmetric? It would be nice if we could cut our workload in half. Are we good? Any questions?
Will it work for any number of variables?
Yeah, you can have symmetry in 3 or 4 variables. And if you notice that a function is symmetric in, say, 3 or 4 variables, you only need to get one of the answers the hard way, and then you could figure out the other answers. Yeah.
So it pays off even more.
Probably, yeah. Because if you have to do, if there's a, well, let's jump right to that since you said that. Let's look at functions of more than just x and y. Let's look at functions. Oops. Didn't realize I had so many bits of paper going on here. Hi, this question here is w equals the natural log of x plus 6y plus 10z. Now this is not symmetric. Would you agree if you switch the x, y's and z, wouldn't you get different looking functions? It wouldn't be the same as that one. Now if it was 3x plus 3y plus 3z, then it would be symmetric, right? If it was x squared plus y squared plus z squared, it would be symmetric, right? Actually, maybe I should do a symmetry one after this one. Now, you want to do the partial derivative with respect to x. It's a chain rule, it's 1 over this ugly lot, right? Times the derivative with respect to x is what, just 1? So the answer would be 1. If you wanted to do the partial derivative with respect to y, and if you wanted to do the partial derivative with respect to z, you're all happy about, you know, it's a very easy question to do, so I'm not spending a lot of time. There's not an awful lot going on. Couldn't I have a function of 20 different variables? Right? Theoretically, I'm running short of letters of the alphabet by then, right? But theoretically, couldn't I? And couldn't you do a partial derivative with respect to x, y, z, w, p, q, r, and whatever other letters were there? Typically, when a function gets to have too many variables, technically speaking, that is a function of 100 variables. But we don't call them x, y, z anymore. Do you see? We just call them x1, x2, x3. But they are considered independent variables, right? x1 is a different variable than x2 is a different variable than x3. So if you're wondering how do you have, or how would you write a function with 100 variables, that's the most likely way to do it. I just made this one symmetric, by the way, just to make my life easy, right? In case you're curious. Right, let's do a symmetric one in 3 variables. So w is going to be x cubed plus y cubed plus z cubed squared. Symmetric functions, for want of a better word, don't they have a look to them? They just kind of look symmetric, for want of a better word, right? Balanced, there's another word you might want to use. Isn't this function symmetric in x, y, and z? Great. So shouldn't I only really need to find one of them and then I can figure out what the other two for free? Any particular one you want me to get, x, y, or z first?
Actually, I have a quick question. So
Yes.
if it was symmetric with x and y, like say z was to the 4th or something, would you be able to find what? Like
Yes.
you wouldn't be. I'm sorry. What'd you say?
I was agreeing with you. I think we must have a time lag in the voice line.
Oh, okay. So could you find could you use the symmetry to find the x and the y but not the z?
What a cool question. Very cool question. The answer is yes.
Oh, thank you.
That's a little subtle. And if you can handle it, I'm cool with that. I tend to not do it because people will say, but it's not symmetric, but you're doing the rules that it was, and then they want to do it with the Z guy that doesn't work, right? But if you cope, you know, the fact that you thought that through means you could cope with that. Yeah, certainly you could do that. Right. Would you agree this fella's a general? Would you want X, Y, or Z first? Don't matter.
Why?
Yeah. We'll do it that version of notation. Multiply by the power. Reduce the power by 1, so you don't write 1. And differentiate with respect to y. You get that. Make it look pretty. Now, if I want to do the partial derivative with x, and finally the partial derivative with respect to z, would you agree that I could just use this as my template? Agreed? And figure out who goes here and who goes here. So what do you think the answer with respect to x would look like?
6x squared. y squared plus x, or x
Yeah, all the other
cubed
stuff.
plus.
Agreed. And the stuff, right? Now, yeah, technically x cubed, y cubed, and so on. You may write the order down differently, but to me, I know they're going to end up being the same thing, so I just write them in the x, y, z. You know, for it just looks prettier in alphabetical order, doesn't it? For want of a better word. Right, you see, in that case, then we could do quite a lot of cool stuff. Are there any questions about more than 2 variables now? That you could do it with 10 or 12? Now, you're not going to get a lot of practice on anything, so don't expect every second question to be symmetric. It would be really nice if they were. But if the odd question or two is symmetric, you can use that little shortcut to do it. So now, in the last, 7 minutes, I'm going to show you a new problem. We're going to go back to the functions that look like this. We're going to find partial derivatives with respect to x and with respect to y. We've done those, right? We're good at those, hopefully. Now we're going to have to deal with functions that look like this. Where the z is not separated, it's mixed up with all the other terms. The equivalent to this would be a way back. I know it's a long time, but remember implicit differentiation in Calc 1. Remember those questions where the x's and y's were jumbled up? We're going to use implicit partial differentiation. And the reason that I'm going to have to use it is because it isn't z anymore. It's not z equals a function of x and y, but z squared, x squared zy, you know, things with z's mixed up with the other 2 variables, right? So whenever you see a question like this, you know you're going to have to use implicit partial differentiation techniques. So let's suppose the question said, find the partial derivative of z with respect to x. Not unusual for it to ask that. Then just rewriting the question again, and I'll show you how I would tackle it. Step 1. Take each separate piece, including the 10, and do a partial derivative of that term with respect to x. So the number 10 would get you 0. If you do xy with respect to x, don't you get y? If you do x squared with respect to x, don't you get 2x? So far, so good. Now the sneaky part. I'm now going to differentiate z cubed with respect to x. And that's where the implicit bit kicks in. Can you remember in Calc 1, if someone went and said to you, do z cubed, wouldn't you get 3y cubed dy, 3y squared dy by dx? Can you remember? That's how implicit differentiation worked. Now let's do it with z cubed. You differentiate z cubed, you get 3z squared times that guy. So far, so good.
Yes.
Right, now, pretty standard step. Step 2 now. Solve for dz by dx. In other words, rearrange this information so that dz by dx is equal to whatever it is, right? Now, to do that, we are going to use another made-up name. I call this, as long as you do it to both sides, it's okay rule. That's a long name for it. As long as you do it to both sides, it's okay rule. Tell me some things to do to both sides that's going to get that a little bit nicer. I don't need the whole answer yet, just some of the things you should do first to get closer to that answer.
Subtract 2x and y.
And now, what should you do to finish the whole process?
Divide by 3z squared.
Well, I prefer if it was z squared, but Americans can't
Z.
speak properly, so we'll do that. And there is your answer.
I do have a question.
Yes.
Would we want to solve the original function for z and then substitute that in for z, or is it okay that this is a function of, that this partial is like a function of 3 variables?
Yeah. I think Webber's, the answer you won't like, yes and no. Both are correct. Leaving it as z is quite clean. And in many implicit differentiation questions, don't you end up with answers that look like this? And you don't say, well, should I turn the y into a function of x and rewrite the entire answer only using x's, which is essentially what you're saying. So this is a valid answer.
Okay.
In some situations, I could rearrange this. It would be downright ugly to do it, but couldn't I rearrange this and solve for z?
Yeah.
And that ugly z could go there and squared. And if you had did that mathematically, it is correct. So that's yes, you can do that. Or you can leave it alone. And the answer is yes, you can leave it alone. So that's why I'm saying it's yes and no, or no and yes, or whatever, right? So both are acceptable. Me personally, I think that's prettier. Would you agree? It's just cleaner, tighter. And so that's the form that I think you should leave it in. Any other questions? So that was a mixed up guy. We have run out of time. Darn it, I was wanting to do one more, but time got ahead of us. We learned some cool stuff today, didn't we, Eleanor? We like symmetry. We should get t-shirts saying we like symmetry. It's a pity, I'm just moving my brain here. Do you know symmetry should have been a symmetrical word? Shouldn't it have been a palindrome? You know, the word that we use for symmetry should have been a different word, and it should have been a palindrome. You know, a word that reads backwards to frontwards. Wouldn't that have been a cool? Yeah. See, the guys that were who decided to call it that. Do you know if they'd thought a little bit harder, they could have come up with a better name? Couldn't they have called it an ABBA?
That's a good point. And
Yeah.
phonetically is not spelled phonetically.
That's true. Yeah. Oh God, I'm gonna have to tell you a bad joke, and then we'll. While I'm thinking about this bad joke, will you all say hi so we can get attendance? Did you hear about the dyslexic, insomniac atheist? He spent all night awake thinking, is there a dog?
I was wondering where that was going.
Now that you've found out, you're regretting that you waited to find out. Okay, guys, officially officer will be next period, but I'm going to have to close this off so that I can open up the Zoom meeting for officers. So if you do have an officer, in your case, we'll make a special exception. So you just wait behind and I'll do the thing, right? And for the other classes, they can do that. Is there any questions for the good the thing? We good? Our first Zoom lesson is on Canvas, and this one will